Hello everyone. So, good evening to this class. This is the week 6 discussion class for design of photovoltaic systems. And this course is being taken by Professor Alumanan from Department of Electronics Systems Engineering from IIC Bangalore. And I'm Ravi Kumar from IIT Bombay. I'm a PMRF research scholar. So, before starting this actual discussion, we will have a recap what we have learned and then how this week is related to all those steps. So, in first weeks or like from the starting, we have understood the basics of solar PV. Then we understood solar PV module performance. Then all the affected parameters, affected or impacted parameters. Then we have also studied like series and parallel connections. Combinations of solar cell or modules. Then we have also studied solar radiation, different angles, solar radiation, solar irradiance on a flat plate at any tilt angle at any latitude on the earth. Then we have calculated solar PV module requirements. Also, battery requirement. But all the above things we have done on a particular condition. We assumed that solar PV is working at maximum power point. It means to calculate each and all these requirements, we have assumed that our solar PV system is working at the maximum power point. So this week's discussion is entirely based on this MPPT tracking. Means how can we track or how can we get the maximum power point on a IV characteristics of a solar PV module. So this is all about the recap and the requirement of today's lecture. So what is this MPPT? This MPPT means maximum power point tracking. It means on a solar PV IV characteristics, we need to identify the point at which the maximum power can be obtained. Let us understand from this. This is a simple IV characteristics. Here we have VOC, here we have ISC, here we have VOC, and this is the point which we are talking about. It is the maximum power point. The power at this point will be V into I. Here V is 0, so 0. Here power will be V into I. Here I is 0, so it will be 0. But at this point, the power will not be equal to 0. But this power will be P max. It means at this particular point, the power can be obtained, will be the maximum power. So it is all about this tracking this point. How can we get this particular point to work upon? So we all know this depends on what factor does it depend? It depends on the resistance of the load. If this is our solar cell, let's say, so this is our R load, and this is a varying. So by varying this R load, we can trace this point on this IV characteristics. So at a particular value of this RL, we will obtain this point where the power can be obtained. That will be the maximum power. So on this IV characteristic, we also can see from this. So this is the IV characteristics. So what we do, we will just have a load line. This particular line is the load line. So in this load line, it is 1 upon RT, and RT generally we say the resistance across these terminals. So in this case, RT will be equals to RL. If it is the slope, it is the slope. So if RT is equals to 0, then slope will be infinite. If is RT equals to infinite, this slope will be 0. So this particular condition, RT is 0, slope will be infinite. So if this RT is 0, let's say this RT, so maximum power point, so this will be the maximum current condition. So this point will be this particular condition. When resistance across the terminal is 0, then slope will be infinite, and at this condition power will be 0 but current will be maximum. For the other point here, RT equals to infinite, then slope will be 0, and at this condition our I will be 0, V will be VOC, that is maximum. So this is about the tracing the IV, tracing the maximum power point. This is the same circuit which I was talking about here. So what we do to obtain this particular point using this load line, because our load connected to a solar PV system is constant, it means the resistance is already defined. So we cannot change this R naught to track this IV characteristics or to trace this maximum power point. So we have some device in between which do one thing, which changes the resistance towards this RT, towards this PV system. And by changing the resistance across these terminals, we obtain this particular point. So these are the devices which are known as trackers, maximum power point trackers. We will understand there are like mainly three types of trackers which have been used in these solar PV systems. We will understand them. So first of all, just understood, this is all about the maximum power point tracking. We cannot change the resistance of the load. That's why we need something in between which can have a variable resistance at the VT side and which can make the solar PV to work upon at the maximum power. Okay, let's move next. So first of all, this tracker in this category, first we have boost converter. Converter is just converting DC into DC only. So we usually say converter. So it is saying the boost converter. It means voltage will increase here. Boost or like buck, it's all about the voltage. So this is a particular kind of tracker. Let's see the circuit diagram. So this is our load and this is our VT. We need this VT to change, or we can say RT here, because RT and VT will be interdependent. We need a resistance across this terminal to change, to track the maximum power point. So on this boost converter having component like inductor, this diode, then a switch and capacitors. So this is the basics of this boost converter. Even you have understood from the lecture only. So what is important here? Important are the relations. So for this boost converter, the V output towards the load will be related to this VT. VT means voltage across the terminal. So this is the formula. This is the equation which relate this VT with the V naught. Similarly, IT, then using this 1 and 2, we can get the relation between this RT and R naught. Now R naught is the load resistance. And it is fixed. It is fixed, but we need RT to vary. So if R naught is fixed, we need this RT to vary. Then we have another parameter here, that is the D. So by changing the value of D, we can change or we can vary this RT. And if RT will vary, then we can track the maximum power point. So this is all about the boost converter. So here there is a problem with this boost converter. What is the problem? We will see. So let us understood like this. This is a solar PV panel. This is our load and this is the device, which is here is the boost converter. So the relation says this: R naught equals to RT. I can write here. If D equals to 0, then RT will be equals to R naught. And if D equals to 1, then RT will be 0. It means it can vary RT from 0 to R naught only. So we can track this characteristics from this infinite slope to 1 by R naught slope. That is this one, 1 by R naught slope. So this is the portion which left uncovered. We cannot track this particular condition here in the boost converter. here also you can see. And even if this R naught, like in this condition it was here 1 by R naught, but let's say this R naught is having very large resistance, so 1 by R naught will be here, so it will be just before the MPPT. It is our maximum power point. So it means we are not reaching to this maximum power point. It is the limitation of this boost converter. Okay, so if boost converter is having a limitation, so can we have some other converter as well? Yes, we have one more converter, that is buck converter. Let us understand what is this buck converter. So in this buck converter, these are the components: switch, diode, capacitor and inductor. So similar way, by like derivation, we got this relation between this V output or V load with the VT, that is the terminal voltage, then I with the I. TAV means this current that is coming from the solar PV module, and using these two equations we obtain the relation between this RT and R naught. Now can we get the points which were not covered in the case of a boost converter? So let's see. If this is the relation between RT equals to R naught by D square, so for D equals to 0, RT will be infinite and 1 by RT will be 0. For D equals to 1, RT will be equals to R naught, or 1 by RT will be equals to 1 by R naught. So it means from 0 to 1 by R naught. From 0 means from this point to 1 by R naught. Only this portion we can track. So we can track this portion. So this portion we cannot track using this buck converter. And similarly, if R naught value is having like this, it is below this maximum power point, then we cannot track the maximum power point. That is the limitation of this buck converter as well. So now you understood like this. This is the IV characteristics. So one portion is giving this thing. We can track this area. With the another one, we can track this area. So I think using the both, we can track the entire IV curve. Yes. So using both at a time, boost as well as buck converter, we can trace the entire path. How? Let's see. So now the third one is the buck boost converter. So it is a combination of both. So now we will be able to trace entire IV characteristics. So this is the circuit diagram. So here these are the components: capacitor, inductor, capacitor, diode and switch. And using this all derivation, we obtain the relation between V naught versus VT, I naught versus ITV, RT by R naught. See, we need 1 by RT to vary from 0 to infinite. Let's see if we are able to do that. So we obtain RT as equals to R naught 1 minus D by D square, and D will vary for D equals to 0 to 1. So if D is equals to 0, RT will be D equals to 0, so 1 by 0 will be infinite, so RT will be infinite and 1 by RT will be 0. And if D equals to 1, then RT will be 0 and 1 upon RT will be infinite. So yes, using this we are able to trace our entire IV characteristics. So our load line will go from 0 to infinite slope. So here you can see we are able to trace the entire IV characteristics. So it means buck boost converter is the converter which should be used in a solar system so that we can trace the entire IV characteristics for looking the maximum power point on in a yes. So we can trace the entire IV characteristics using this buck boost converter. Okay, now we understood which converter should be used, but how do we add the system in our entire solar PV system? What is the interface look like, or how it look like? So this is look like this thing, like this. So we have this PV module, we have this load, we have this converter, that is DC-DC converter. So what we are doing, this DC-DC converter is working on this D. That is our duty cycle here. So we are giving this D to this DC-DC converter and it is changing RT accordingly. But how can we get the value of this D? So for this we have this PI controller. So we get a reference value from here. We give this reference value to the actual value, check if it is right. If it is not right, then the error is transferred to this PI controller and then this change the value of this D. It is look like a feedback circuit. So based on the feedback, it changes the value of this RT, and by changing this value of RT, we are able to work upon, or we are able to extract the maximum power from a solar PV module. So in this lecture, it's all about 3 types of MPPT tracker, and like I summarize here. So we have boost converter, buck converter, buck boost converter. So this is the V naught, that is the voltage across the output or load. I naught, voltage across the input or output, that is the current across the, it is current, it is voltage. Current across the load, it is the resistance towards the load, and this is resistance towards the terminal. And these are the different relations for all types of MPPT tracker. So these all the quantities we will be utilizing in solving the numericals. So let's move to the questions. So first question says, which of the following are isolated DC-DC converters? And these are the options. If you would like to solve these questions with me, you can write in the chat box what is your answer. Flyback converter, yes. Prabhakaran said boost converter, okay.
Now forward and flyback.
Forward and flyback. Yes, Prabhakaran, it is saying isolated. That like boost converter is not isolated. That is a non-isolated DC-DC converter. So yes, we have this flyback and forward converter. Those are the isolated DC-DC converter. Even you can see here, these are the few examples like isolated, non-isolated. See, isolated, non-isolated means like 2 parts of the circuit are not connected directly with the wire, or they don't have any common negative terminal or common ground. So we have this flyback here. we have this forward converter. So both these are the answer here. So correct answer is C and D. Let's move to the next question, which says the circuit diagram of a tapped boost converter is shown here. Switch S is on during the DTS period. It is the time period which is given, DTS. Then the diode is on, and 1 minus DTS is the period when the diode is on for 1 minus DTS period. Yes. Operating under continuous condition. The coupled inductor has a mutual inductance. The mutual inductance for the coupled inductor is given. That is this one, L1 and L2. Find the voltage conversion ratio, that is V naught by Vg, as a function of D, that is the duty cycle. Assume all the components are ideal. Here hint is that the relationship between L1 and L2 can be determined by the turn ratio of the magnetic element. Then find the equivalent inductance and apply the basic volt second balance, amp second balance and energy equations. And these are the options. You need to calculate this V naught by Vg. V naught by Vg. And V naught is this one and Vg is this one. So first of all, calculate the voltage across this inductor at on condition, then off condition. There will be two equations, and then for the entire circle make them 0. Then you will get this ratio. Okay, I am just giving you the first step. So during this DTS period, like voltage across L1 and L2 will be this one, and then for the second and another period, this will be, the summation will be this one. Now you need just one thing, voltage into time plus voltage into time equals to 0. You need to do this only. Do this and let me know what is the answer. Just add them, like Vg plus N2 by N1 into Vg, and addition of this is Vg minus V naught. Multiply this with dts, multiply by this 1 minus dts, and add both the equations and put equals to 0. What is the answer you are getting? It's very simple now. Just Vg plus N2 by N1 Vg into dts plus this Vg minus V naught into 1 minus dts equals to 0. This entire terms will go here, this dts is here, this entire term will go this here, and this dt minus ds will be here, and use this equation and like get this in terms of d. A, B, C or D? Nothing is hard here, like Vg plus N2 by N1 into Vg multiply by dTs plus Vg minus V0 into 1 minus dTs equals to 0. dTs you can cut off, like it will be 0 if you just take it outside. Then we can do one thing, then Vg plus N2 upon N1 Vg into D equals to V0 minus Vg 1 minus D. Put it equals to, now solve this for Vg upon V0. What is asking here? It is asking V0 by Vg. If you just take this,
L. B.
is it which one? B, C?
B.
B. Just take the Vg outside here, so you will get like this: N2 divided by N1 plus 1 D equals to here 1 V0 by Vg minus 1 and 1 minus D. If you will solve this, then you will be getting B, right? Getting B?
Yes.
Yes. Yeah, just solve this, you will get the answer. Answer is B here. So correct answer is B. Let's move to the next question, which says find the terminal resistance across the PV source on the input side for the full bridge converter shown in the figure. The Vn is the input from the PV source, so this is the Vn. Find the terminal resistance across the PV source. Terminal resistance means RT. So it is just asking to calculate RT. What are given? Vn, R0 is the output, this is the R0. D is the converter's duty cycle, and this is the time period. Full bridge, so this here, the converter is full bridge converter, which is being used here in this circuit. You need to calculate this RT in terms of this R0. These are the options here. Just understand one thing, very simple things to do this kind of question. The power input side will always be equals to power at the output side. And this power you can write in terms of P equals to V square by R. And this V ratios you can use direct formula for this buck converter, and you can get it by solving the equations like we did for the derivation has been done for the buck and boost as well. So I can give you directly like V naught by V in here will be 2D end. So you just need to do one thing. You just need to have the conservation of power term here, P input, P output. Put this value in terms of V square by R. Use the ratio V naught by V in as 2dn square. Then calculate the RT in terms of R naught. This power in terms of V square by R are you able to solve this? No? See, P input will be equals to P output, and P input in terms of V square by R, we can write V input square by R. Input means R naught, RT equals to V naught square divided by R naught. Then we need to find out RT, then we can write this as well. RT by R naught equals to V input divided by V naught whole square. I already given this 2dn. Yes, use this here. It will be like RT divided by R naught will be 1 upon 2d n whole square, and RT will be R naught divided by 4 n d ka square. So which options? A, B, C or D?
A.
A. So A is the option here. Next question says, it is very simple question. I won't give you any hint. Why is the input capacitor mandatory at the PV panel output for maximum power point tracking with the buck boost converter? So in the buck boost converter, so I will just show you. The question is asking about this particular capacitor. Why this capacitor is being used in this buck boost converter? This capacitor. So it is asking question number 4. These are the options. Why the input capacitor mandatory at the PV panel output for maximum power point tracking with the buck boost converter, and these are the options. What can be the options? Like what can be the reason? What a capacitor do?
Store charge.
Store charge. Yes. And
I
charge.
think option C is the right answer because inductor current is continuous for Babu Kunda,
Yes,
right?
absolutely right. So it is store charge, that is the current. So we need this input current to be continuous. That's why we use the capacitor. Yes, B is the correct answer. Okay, next question, which says a conventional buck boost converter interface a PV module to a DC grid. Means we have already a PV module connected with this buck boost converter. The converter operates at a duty ratio 0.5. It means D is given 0.5. The average current flowing in the switch of the buck boost converter is 2.5 A. It means ITAV is given 2.5 ampere. The DC grid voltage will be output side. So this output side we can write V naught equals to 48 volt. What is the power in watts supplied by the PV module for the given scenario? It is asking P naught. And these are the options. How can you get the P naught? What is this power? What is the simplest formula you know about the calculation of power? If you have a device, current is flowing through this, any device, then if I ask what is the power across the device or resistance, then how can you calculate this? What is the formula for simplest power?
The power is equal to V into I. For this,
Yes, absolutely. Power
for this was yes,
equals
yes.
to V into I in terms of naught, then we naught is the output. This output is given. Need to calculate this. This can be related with this T average.
So V naught by V is equal to D into 1 minus this formula can be like it.
Yes. See, we already know V naught. We just need to calculate I naught. I naught is already having a relation with this T average with this D. Then use this D, this TAV to calculate this I naught. Then multiply with this P. Then you will get this P naught. Do you need the relation or do you remember it? What is the relation which relate I naught with this IT average?
Sir, I think B is the answer, 121.
Okay, use this. This is the given here. For buck boost converter, the relation between this I naught and IT average is given here. Calculate this I naught, multiply with this V naught, and then get the P naught. I naught will be equals to ITAV 1 minus D divided by D. I naught is given 2.5, 1 minus 0.5 divided by 0.5. It will be 2.5 into 48. You will get this D. How much? What is A, B, or C, or D?
B, sir.
B. 120.
120.
Yes, it is 120. So answer in this case is B. Let's move to the next question, which is also very easy. You need to do it without any hint. So it says, in the maximum power point tracking algorithm, which of the following can be considered the universal DC-DC converter for the maximum power point tracking of PV module as shown in the figure? So this is just the tracking mechanism which I have shown you in starting only, and these are the options. It is asking which condition and why any DC-DC converter can be considered as a universal. Universal means it can use in any condition, not depending on the load resistance R naught. To check the condition, do you need the relation between RT and R naught? Which one? A, B, C or D? B. Saurabh said B. Saurabh said buck boost converter. It gives zero resistance for duty cycle 0 and it gives infinite resistance for D equals to 1. Okay, I am giving you the relations. Check if you are saying is right. RT is the resistance. Now just put the value of D 1 and 0 and tell me A, B, C or D. You just need to check the value of RT at D equals to 0 at D equals to 1. Okay, just tell me which relation will you use? This, this, or this? Yes. Saurabh, you are right. C. Now put the value of D as 0 and 1 and tell me the value of. Okay, Saurabh said C. Okay, now Saurabh is saying C. It gives infinite resistance. It gives infinite resistance for duty cycle 1. RT equals to R naught 1 minus D by D square. If D is equals to 0, in this case, D equals to 0, then RT will be
Actually infinity, sir.
yes.
So option number D.
T will be infinity. And if D equals to 1,
Then it will be 0.
then it will be 0. Okay, now check. It is saying 0 resistance for duty cycle 0. So 0, here we have infinite. So this is not right. Second says infinite resistance for duty cycle 1. No, because for duty cycle 1 is 0. Then D option says for D equals to 1 it is 0. Yes. For D equals to 0 it is infinite. Yes. So option D is the correct answer here. So right answer is D. Got it? Okay. Let's move to the next question, which says the schematic circuit of buck converter is shown here. The value of control VC is this voltage VC. When converter duty is cycle is 0.081. The output resistance R naught is 5 ohms. R naught is this one. The converter tracks the maximum power point of the PV source for constant solar radiation temperature. Find the value of VC when the output resistance is changed to 3 ohms. For the maximum power point tracking of the PV source, assume circuit is ideal, operating under continuous conduction mode, and also there is a relation between D and C. VC is given like this, and these are the options. First of all, just check what all the quantities are given, then check what all the relations are given, then check what we need to find out. So they have given like VC equals to 0.61 at D equals to 0.81 when R naught equals to 5 ohms. So this is the first thing they have already given. Now what they are saying, we see how much when R naught is equals to 3 ohm. This is the second part of the question they are asking. Just use the power conservation formula here. See, it is saying the solar radiation is constant and temperature is constant. It means the power output from the solar module will be constant. Only R node, that is the load resistance, is changing. Write power in terms of voltage and then use the like power conservation formula and calculate the first D then VC. power equals to V square by R. Use this particular relation. And it is saying it is buck converter. So voltage that is output in terms of D relation with V input. What is the relation between V output and V input of buck converter? Because we need a relation, because volt R naught is given from here and V is
D into G.
yes, it will be just D into V. So it means we already have R naught, that is the like output side. We already can get this V naught. We can calculate the P naught as well. Then calculate P naught for this, calculate P naught for this, equate them and find out the value of, you will be getting the value of D here, and then you will get the value of VC. P naught in first condition, then P naught in second condition, equate them, find out the value of D. What you are getting? No? Okay. So power is V square by R. Here we can write this. See, this is our, this VC is from here. So what we can do, we can write in terms of a V input only. Because voltage will be constant input side, so this we can use V input. So it will be like D V input square divided by R naught. D is already given 0.81 into V input square divided by 5. So this is the one equation. Another one is for this thing, we need to calculate D into V input square divided by 3, because in the second case our R naught will be 3. Now you need to do one thing. I'm going here on this thing. So 0.81 into V input square entire divided by 5 equals to D into V input square divided by 3. Solve this, you will get D here. What is the value of D? Because V input will go on here, you will get 0.81. D square will be 0.81 square into 3 divided by 5. And you just take the under root, then you will get D. Just do the mathematics. I will also do the mathematics here. Point 81 square divided by 5 into 3.31366. No, yes, take the under root as well, because it is the D square. So now this is the D square. You need to find out the D. Yes, exactly. If I am talking about this, it is 0.627. This is the value of D. Now we have a relation like D equals to Vc plus 1 by 2. Put this D here, calculate this Vc. .25. Yes, so it's like this. 0.62 into 2 minus 1. 0.25. Answer is A. Correct answer is A. Okay, let's move to the next question, which is very simple. It says, what is the input impedance seen by the ideal boost converter R naught in the output resistance of the converter, and D is the duty ratio. These are the options. It is asking about the boost converter, the relation between RT with R naught. RT in terms of R naught. This is the table. So let's match this. it is saying boost converter, then we will see the boost converter. It is saying this thing. Yes. Yes, Saurabh, you are right. It is 1 minus d square A. A is the correct answer here. Let's move to the next question, which says, what is the input impedance seen by ideal buck converter? It is asking about the buck converter. These are the options. So we need to find out RT in terms of R naught. But for buck converter. B. Okay. Saurav said B. This is the table for the buck converter. RT related to this. Yes, B is the correct answer. So this table is very handy. You have all the relations at a place and you can use them. Now let's move to the next question, which says, what is the input impedance seen by the ideal buck boost converter? R naught is the output resistance, D is the duty ratio. These are the options. It means RT in terms of R naught. C. This is the table. It is about buck boost converter. This is RT relation with R naught. 1 minus D by D whole square. Yes, correct answer is C here. Okay, let me check one thing. Questions we are done for today. I am just checking one thing to show you if things is there. Yes, like we are done for this class. Someone's mic is on. Let me check and make it. So I was talking about this PV system, like pveducation.org. So have you like gone through this website? Yes or no? See, this is all about the MPPT tracking. We have three like main. Okay, no. I'll take you. Just wait a minute. Yes, it is visible now. Okay. So I just wanted to show you some like the benefits of going through this thing. So here you can understand the things by just seeing the animations like this. So this particular website is having so many animations. Means if you are not able to like imagine, then you can refer those like GIFs or animations from this website. And like I'll just show you things. And to just go through, just write PVCD-ROM. It is like welcome to PVCD-ROM. You will go here. So this is the PVCD-ROM. Then we have starting from the starting, that is the solar energy. What is the solar energy and all? Means this website is dedicated to the solar photovoltaic, even from the first thing, the sunlight or the solar energy, and it goes to this like what are the properties of sunlight, black body radiation, and you will get like more animations, more interesting things here. I'll show you. All the things are here, like atmospheric effect, what is the atmospheric effect, how much radiation comes. Like here you can see, you can just play with these animations and you can see this is AM0 radiation, this is AM1.5 radiation, this is visible length, this is, you can remove this visible length, black body, this is the black body radiation, and this is all about the basics. Then we have this air mass calculations. Many calculators are there are like n number of calculators. You can just put the values and get the answer there. See the motion of sun in a fantastic way. So using this particular website, you can like understand the things in a very lucid manner, and you can understand the things in better way. See, this is the sunlight on a flat plate. You can change the angle of flat plate like this. See, this is the tilt angle. Even like declination angle, I'll show you. See, this is the declination angle. It is 0 here, maximum here and maximum there. This is how Earth having sunlight. Like this particular condition, just now the declination angle is 0. This is maximum other side, and then it will be maximum to the other side. And like for the Earth perspective, we can see this like this. See, elevation angle, how suns go up, then afternoon, the sunrise and sunset, how it looks like, how the radiation come, what is the zenith angle, how it changes, what is the relation between zenith and elevation. All the things are there. Then this azimuth, what is this azimuth angle? You can see when it is 0, when it is maximum, when it is negative, when it is positive. You just play with this, you will understand the things. At least go through the animations. If you are not reading the entire website, it's okay, but just go through the animations. And even like for the semiconductor and all, this is all about the solar radiation. Like I'll show you the things in the semiconductor. Like this. Where is starting from this ingots of silicon to the solar cell? What are the basics? What is the semiconductor? What are the semiconductor materials? The structure, conduction in semiconductors. See, these are the electron and hole, how they are free, how they are not free, like this. All the things are here. What is the band gap? See, conduction, distance, electrons, energy. It is going up. Next. So this is the way like conduction takes place in a semiconductor device. Even like this is all about the semiconductor. I'm just showing you. We just go through it once. See, valence band, conduction band, and even like this is PN junction. Yes. Because solar cell is a PN junction device only. So we will see some animations from PN junction like this. These are the PN junction. This is the boundary. Now we will remove the boundary. So how the electron and hole recombines. How the diffusion region is here. How this diode works. This is the PN junction diode. You can see electron drift, electron diffusion, hole diffusion and all. Now see the very interesting thing, that is the biasing. See, I'll put it equilibrium condition. It is a equilibrium condition. I will forward bias it. See, this is the forward bias condition. I'll reverse bias this. This is the reverse bias condition. So you can see these things here, like electron diffusion, forward bias, which is the like dominating here, which is like not dominating, like this. So this is all about the semiconductor, diode equation, solar cell operation. Come to the solar cell operation thing. Solar cell operation. So flow from like solar radiation. Why it is not moving? Is there any issue with the internet? Internet is there. Okay. See, this is the IV curve. Even you can understand better here. So this is the IV curve of single diode. You will see when light is coming, how this IV vector is changing. More light, more change. Then we are taking the reverse. So these are the things to understand. Even the efficiency, detail, resistive, impact of both series and shunt resistance, you can understand here. See, series resistance, how the IV characteristics changing. This is the impact of series resistance, and this is the impact of shunt resistance. Like this. This is the impact of shunt resistance. The impact of shunt resistance is this one. Even like in the design part, you have everything. Anti-reflective coating, optical properties, light trapping, recombination losses, each and everything you can get from this website. Then how silicon wafers or silicon solar cell are manufactured, what are the types of like different like these are the fabrication processes of silicon, multi-crystalline wafer slicing and all. Then production line, texturing, emitter diffusion. It is like from starting to the end. Firing, screen printing, testing module, and few even interesting videos as well, like this. These are the actual videos. Robotics arm, which is like sorting this solar cell based on their properties and all. These are multi-crystalline solar cells. Then from this, after this testing, they have PV module. So they have connection like this, and using this connection, they make the module. If you are interested in like knowing about the solar photovoltaic from the bottom of art, then you can use this website. What is PV module? What are the components? How they are like encapsulated? What is the temperature they require? What is the frame? What is the rear surface? What is the packing density? All the things are here. These are the different packaging density, why the space between the solar cell is important, what happens if this packaging in like density is decreasing or increasing. Temperature effect, characterization. Then you also have characterization. So the motive, like the objective showing this website is just to have n number of animations, n number of pictures, n number of videos to understand the real things, how solar cells are being built, how solar cells are being used, what is the basic understanding, everything you can get from this website. So that is the only motivation behind telling this. And this is having n number of things you can play with this website, you can play with the animations. Once again, I am just putting the video channel link here, and I am just pinning it in case you are not able to come on the time. So I will upload all the videos on this YouTube channel, and like from different courses as well. Many videos are there. Even the earlier week lectures videos are also there. So like I am done from my side. we will meet in the next week, that is the next Friday, and we will have the discussion on the next week lecture. I just want you to be attentive. I just want you to go through the lectures beforehand so that these discussions like may be more interactive and you solve the questions. You just at least try the questions. Thank you everyone. Take care.